Hello everyone. Welcome to this session on AWS VPC. Today with this session we are going to take a deep dive into the concept of virtual private cloud and what it is. But before we begin, make sure to hit that subscribe button and bell icon so that you never miss any update from Intellipaat YouTube channel. First of all, we'll take you through the agenda for this session. We'll begin this session by understanding what is VPC. Then we'll understand why virtual private cloud was introduced. Once done with that, we'll explore IP addresses and the concept of subnetting. After that, we'll cover the basics of AWS VPC terminologies. And finally, we'll delve over how you can launch instances into VPC. I hope I have made myself clear with the agenda. So without wasting any time, let's get started with this session. We will start this session with a very basic question: what is VPC? To sort of visualize this term in significance to the real world, we'll go back to the pandemic days. Do you remember standing out in line to gain access to grocery stores, hospitals, and even ATMs? I believe you guys do. In those times, we were opting services by getting ourselves contained in our own private sanitized space or by following norms of social distancing. Almost similar to this, enterprises want to use all the services available in AWS, but they want to do it in their own private sanitized space. And this private space is provided to these enterprises by a service in AWS known as VPC. VPC leverages the AWS users to create their own network and sort of use all the services of AWS as per their requirements. Now to define VPC formally, let's consider this illustration over here. The blue box isolated inside the AWS region is VPC. That means the VPC will always be defined inside the scope of AWS region. Furthermore, there are many availability zones within the region itself, as you can see here. So the thing to note here is that these VPCs can spread over all the availability zones within a region. In this particular example, there is only one availability zone, but remember that region can contain multiple zones where VPCs can be spread. Another thing to remember here is that these VPC networks are generally large, and in order to have more control over this network, it is further divided into smaller groups called as subnets. If I combine all the points that we discussed, an Amazon VPC or virtual private cloud allows you to create a logically isolated area of the AWS cloud from which you can launch AWS resources in a virtual network of your choice, and you can have a total command of your virtual networking environment, including the ability to choose your own IP address range, create subnets, and configure route tables and network gateways. In your VPC, you could employ both IPv4 and IPv6 for safe and convenient access to resources and applications. Moving forward, let's discuss why a VPC is required for an enterprise using the cloud or migrating to a cloud. The most important concern is privacy, security, and protection of proprietary data. I mean, there are many companies out there using AWS cloud services, and being in the public network of AWS can put data and operations of organizations at risk of leakage. And on a public network, there will always be a high traffic, plus you won't be able to control the entirety of a network, right? That is the reason why all organizations want private networks of their own over cloud service. And this is the point where VPC steps in. VPC provides an extra layer of security wherein companies can define their own network. Not only that, but companies can connect with their storage, network, or developmental instances or services in no time. During the time when you create AWS credentials, a default VPC gets created. But in corporate environment, customization of VPC is quite crucial. The tools to customize the VPC will already be made available by AWS. And by making use of these tools, you can explicitly create subnets, security groups, internet gateways, etc. Before we dive deeper into the technical jargon of VPC, let's first take a step back and understand the basic terms such as IP address and the concept of subnetting as well as its significance. First thing first, what is an IP address? What is the purpose of an IP address? Don't worry if you don't know any solution to both of these questions. the vast majority of computer users are also unaware. And to be honest, that's just okay. You never have to think about it, even though it is your internet passport. If I'll have to simply define it, I would say an IP address is a network address for your computer so the internet knows where to send your emails, data, pictures, packet requests, and almost everything online. The IP address is a fascinating product of modern computer technology designed to allow one connected computer to communicate with another device over the internet. IP addresses allow literally billions of digital devices connected to the internet to be pinpointed and differentiated from all other devices. Just like you need a mailing address to receive a letter in the mail from a friend, the server that has stored data you require access to need your IP address to sort of send that data to your computer. You can relate this IP address with your own mailing address. Every house has a specific number assigned to it so that the drafts and mails of post will reach you precisely. Similarly, for internet content to reach you over the large pool of smart devices, you have been assigned with an address named as IP address. Right now, there are two types of IP addresses used in the market. The first one is IPv4 and the second one is IPv6. The most common type of IP address is known as IPv4, standing for IP version 4. Here is an example of what an IPv4 address might look like. An IPv4 address consists of 4 numbers, each of which contain 1 to 3 digits with a single dot separating each number. If we convert it into binary format, it will resemble 32 bits. Each of the 4 numbers can range from 0 to 255. This group of numbers creates the unique address to let you and everyone around the globe send and retrieve data over our internet connections. But the question here is, are these IP addresses enough? Will we ever run out of these IP addresses? Guess what? We already did. The past decade had seen explosive growth in the number of devices connected to the internet, from mobile phones to tablet, computer, and wireless handheld devices. The format of IPv4 wasn't designed to handle the sheer number of IP addresses we needed. Fortunately, there was backup IP address type waiting in the wings named as IP version 6. IPv4 supports a maximum of approximately 4.3 billion unique IP addresses, but IPv6 supports in theory a much higher maximum number highlighted on your screens. If your eyes glaze over when reading that number, just know that we will never run out of IP addresses ever again. An IPv6 address consists of 8 groups of 4 hexadecimal digits. Here is an example of IPv6 address. I hope now you guys understand what an IP address is. In the context of cloud, you can imagine IP addresses the same way. Cloud is a completely virtual framework which allocates resources to its users once requested. But to sort of provide more abstraction and security, users prefer the unique IP address to be assigned, so that they can create multiple subnets to sort of control the enormity of a private IP address. Now that we have mentioned the term subnet, let's also discover what it signifies. So guys, to sort of contemplate the process of subnetting, we'll use the IPv4 address as an example. So as we had seen in the previous section that IPv4 is a 32-bit IP address, and inside this IP address some bits are assigned to the network and some to the host. Also, there are 5 classes these IP addresses have been segregated, naming class A, class B, class C, class D and class E. For this particular session, we'll discuss class A, B and C. In class A, you'll have the first 8 bits as network bits and all other as host bits. The range for this class will be 0 to 127, and the sample class A IP address will look something like this: 72.123.21.4. Then we have class B, where you'll have 16 bits as a network bits and 16 as host bits. The range for this class will be 128 to 191, and the sample class B IP address will be 180.129.21.4. Whereas in case of class C, you'll have 24 bits as network and only 8 bits as host bits. The range for this class will be 192 to 223, and the sample class C IP address will be as shown on your screens. Now let me sort of formalize the concept of networking with a real life illustration. Consider a train here. Let's say there are only 4 compartments in this train, and each individual compartment can host a maximum of 100 passengers. Furthermore, each compartment has been assigned to different cities that lie on the way. Let's say the train starts from Goa, then visits Bengaluru, then goes to Pune, Mumbai, and Delhi. So, for each different city, a different compartment has been assigned. What I mean by that is, for people going to Bengaluru, there are only 100 seats available which will be allotted in compartment 1. Then for Pune, we have compartment 2 and so on. Now let's say we have this booking data here. For this train, 100 people are going to Bengaluru and Pune. Whereas for Mumbai, we have 160 bookings and for Delhi, we only have 20 bookings. But the problem is, we only have 100 seats available in Mumbai compartment. So what can we do? Well, we can transfer the 60 seats from Mumbai compartment to the Delhi compartment to cater all the customers, and still we'll end up having some empty seats on the train. Furthermore, by doing this, we'll actually stop unnecessary wastage of resources, right? And this is the exact way subnetting works. It helps you utilize your network bandwidth more efficiently and intelligently. You have seen till the time that we have predefined network and host bits for classes such as class A, B and C. But suppose you have a requirement wherein you do not require so many networks to get vested or so many hosts to get vested. In that case, you divide the particular network into multiple subnetworks based on the usage, and that is precisely what subnetting is all about. Now let's come back to IPv4 subnetting. There are few factors you should know before we actually take up an example of subnetting. The first thing to note is subnetting mask. Subnetting mask will identify the class of your IP address. For class A, the IP address will be 255.0.0.0. For class B, it will be 255.255.0.0. Then for class C, it will be 255.255.255.0. Then we have classless interdomain routing or CIDR. I want you guys to reflect on the train example we discovered earlier. In that example, we saw that we could utilize reserve bits for better management of the network, and the use of those excess bits is represented with the CIDR. For example, let's say we have this IP address over here, 202.201.150.10, and it has /27 extra mark. This /27 mark represents the CIDR notation. From the range of given IP address, we can deduce that this particular IP address belongs to the class C. However, if I consider /27 mark, then this IP address does not belong to class C. It utilizes 3 extra bits than the network bit limit of class C. Then we have a network ID. Every subnetwork will have a network ID at the beginning of IP address, and this ID will link the subnet to the large network. It is the first address in the network. I mean, still it cannot be a random IP address, but it must match with the network mask in a binary view. Here is a sample example of network ID for your reference. Next term we have is broadcast ID. In any network, when we need to send data to a host device connected to the network, a router uses broadcast address. Additionally, every network has one unique broadcast address. Here is an example of broadcast address. The process of sending data to every device or node connected to a network is known as broadcasting. Moreover, there is only one source in broadcasting, and other host devices are the destinations. Next, we can simply replace the last bit of a network address, and that would turn into a broadcast address. Therefore, we can determine the broadcast address of any network using the subnet mask and IP address of that network. Next, we'll take an example of IP address and derive possible number of subnets and host IP addresses. The IP address we have here for this purpose is 205.150.65.0 with CIDR notation 26. Let's first figure out the IP address in binary form. By looking at this CIDR value, we can say that there are 26 bits that represent the network and 6 bits that are representing the host bits. Now, if we put this data in a binary format, we can easily figure out the subnet mask. How? Well, we can deduce that this network uses 2 extra bits than class C. Hence, it will have 255 at the mask values for first 3 octaves. But for 4th octave, we need to figure out the value. Since there are only 2 network bits here that take 7th and 6th position from right to left, hence, we'll have to calculate the result that sums up 2 to the power 7 and 2 to the power 6, which is 192 in this case. Hence, our subnet mask will be 255.255.255.192. Now the next part is network ID. Network ID is the AND output of IP address and the subnet mask. So if we carry that out and convert binary form into decimal form, we'll get the network ID, which is 205.150.65.0. Next factor that we can figure out are possible number of subnets and possible number of hosts. So the number of subnets can be calculated by formula 2 to the power n, where n stands for the number of network bits in the finally network utilized octet. In this case, it is 2. So the possible number of subnets will be 4. Whereas the number of hosts can be calculated using formula 2 to the power n minus 2, where n stands for number of host bits in the final octet. Here we have 6 host bits. So the number of hosts we can have for this particular IP address will be 62. Now the next thing we can figure out is the broadcast address. Usually the address that comes after all possible hosts is considered as broadcast address. So after 62 hosts, the 63rd address will be broadcast address, which will be 205.150.65.63. I hope with this example you guys have a clear idea of what subnetting is. Now let's come back to VPC. First thing first, let me tell you about a few basic components of VPC. The first one is Internet Gateway and NAT. What this does is, it logically enables routing of traffic in the public network. That is, it gives us a gateway like a firewall from which our virtual private cloud can connect it to the internet. Then we have DNS. It is basically a standard which resolves names used over the internet into IP addresses. Next up is Elastic IP. It is a static IP which never changes and it only supports IPv4. An elastic IP address is a reserved public IP address that you can assign to any EC2 instance in a particular region until you choose to release it. Fourth up is VPC endpoint. It is a horizontally scalable, redundant, and highly available virtual device that allows communication between EC2 instances in your virtual private cloud and other AWS services without adding availability concerns or bandwidth limits to your network traffic. This is one of the key features of VPC. Then we have network interface. Basically, it is a point of connection between a public and private network. Then we have egress only IG. This is the thing which allows only outbound communication from EC2 over IPv6. Another important term in VPC is route tables. Basically, it defines how traffic is routed between each subnet. Finally, we have VPC peering. It is a connection between virtual private cloud instances. Now that we know the terms, understanding VPC will become quite straightforward. While initiating this session, we mentioned that VPC may contain the large network. And in order to have a better architecture within this large network, we may need to divide it into smaller networks. And that's why we explain the concept of subnetting to you guys in details. Basically, the subnetting is a simple notion that allows you to have multiple networks within one large network, and the smaller networks within the networks are known as subnets. Initially, AWS creates the default VPC for you guys, which will have 32-bit size and CIDR value at 16. To sort of give you an example, this is how a sample IP address will look like: 172.31.0.0/16. This network will provide up to 65,536 private IP addresses. Next, it will also facilitate you with a subnet that has CIDR value 20. Now, each subnet with such a CIDR value can provide up to 4096 addresses. This is enough to sort of represent the enormity of AWS VPC network. Moving ahead, let us contemplate how you can launch instances into VPC. As mentioned earlier, VPC is a logically isolated network assigned to your account. Every compute resource, in other words, AWS EC2 instance, will be launched into a VPC. That means without it, you cannot actually access the compute resources of AWS. If you guys are new to EC2 terminology, then let me tell you guys, it is a virtual machine that represents a physical server for you to deploy your applications. Instead of purchasing your own hardware and connecting it to a network, Amazon gives you nearly unlimited virtual machines to run your applications while they take care of hardware. Basically, it is a framework providing computing resources. When you launch any instance and specify a VPC, the first thing will be identifying the subnet where this instance needs to be launched into. If no subnet is selected, AWS will pick the default subnet within the selected VPC. Once your subnet is identified, the next step will be identifying an availability zone. Users can pick the zone or let AWS select a zone for yourself. Once the instance is created within the VPC or subnet or the availability zone, a primary private IP address from the IPv4 address range of the subnet is assigned to the default network interface or ETH0 of the instance. Each instance is also given a private DNS host name that resolves to the private IP address of the instance. If you don't specify primary private IP address, AWS selects an available IP address in the subnet range for you. When you launch an instance into a subnet that has assigned public IP address attribute enabled, a public IP address is assigned to the primary network interface that's created for the instance. A public IP address is mapped to the primary private IP address through network address translation, or what we commonly call as NAT. These public addresses will change whenever you stop an EC2 instance and start it again. While we are on the subject of IP addresses, it's important to note that public IP addresses differ from AWS Elastic IP addresses. An instance's public IP address is drawn from Amazon's pool of public IPv4 numbers. When you stop and restart an instance, the public IP address allocated to it changes, but not during the restart. Elastic IPs are allocated to a user account, then you assign it to an instance. Unless you deassociate it from an instance, release it from your account, the Elastic IP will stay the same. While using this sort of IP, you need to be aware that this IP will cost you if it is not assigned to a running instance. If I have to put this whole process in layman's term, I would consider AWS as an office building. You can think of your office as a multi-story building. Each floor has multiple suites. Each department like HR, payroll can sit in one floor or multiple floors. Every suite has few rooms. Each room has couple of desks where employees work. Now, I will interpret all important VPC terms to this analogy one by one. The first one is region. Think of the office building as equal to a region, just like how AWS regions encompasses other components. The office building is an outer layer that contains many things. Then we have availability zones. You can think of each floor like availability zone. Just like region can have more than one availability zones, our building can have more than one floors. Next up is VPC. Each department in the office is like a VPC. VPC span across available zones in a region, just like each department in your office can span across different floors. After this, we have a subnet. Each suite represents a subnet. Like how each subnet resides only within an availability zone, each suite will be part of the floor and it won't span across all the floors. Finally, we have an IP address. Each desk within a suite represents an IP address. When companies assign a desk to employee, they first look at which department this employee belongs to, then identifies which floor the department spans across, then identifies which suites have open desk, and then assigns one of the desks to the employee. Likewise, when anyone launches AWS EC2 instance, we need to pick which VPC this instance should be deployed to. Then we need to find availability zones. Then we pick the subnet. Then an IP from this subnet gets assigned to our EC2 instance. That's all we have for today. I hope this example was pretty clear to all of you guys out there. If you have any concerns regarding VPC basics, then you guys can put them down in the comment box below, and our 24/7 team of experts will be happy to resolve all of them. Until next time, thank you, and make sure to hit that subscribe button so that you can stay tuned with our channel to learn more about different digital technologies.
Just a quick info guys, if you want to make a career in cloud computing, then Intellipaat provides an advanced certification on cloud and DevOps by IIT Madras. This course is taught by industry experts and IIT Madras faculty. This course is designed to upskill and land your dream job.